So we're looking at a binomial experiment. We're going to compute probabilities for all the possible outcomes. And then we're going to compute the mean and standard deviation using some complicated formulas. N is 3, P is 0.7. That's not what it was on Pearson. N was like 10. I didn't want to add up a whole bunch of numbers for no reason in front of everybody, so I made it a 3. Okay. So 3 times 0.7 is 2.1. So that should be the mean. And then we'll do the square root. And N was 3 times 0.7 times 0.3, like that. I'll get out from the square root. So that's NP, 1 minus P. So 1 minus 0.7 is 0.3. Up it goes. 0.7937, okay. And now I need to get these things. The formula for binomial is NCX, P to the X, 1 minus P, N minus X. And so if we wanted to do 0, we could just do it. I know the answer, but I'm not going to tell you how to do it. Well, it says 0 successes, right? They all have to be failures. So this should be 0.3 cubed, but we won't say that. We'll just start doing the computation. So N is 3. Go math, prob, down to NCR 3. Oh, it was 3. I want to put 0 there. Okay, back up. 0. Then I come over. And then it's times the P, 0.7 to the 0. I do it? Yes. And then times 1 minus P, 0.3 to the rest. So if it's 0, I'll even write it like this just because I can do it. 3 minus 0, like that. So that's NCX, 0.7 to the X, 0.3 to the N minus X. N is 3. Okay, hit enter. Write it up there, 0.27. Okay, 0.027. And the hope is I can go second enter. And I come back here. And I take that 0 and make it a 1. I'm being sneaky here. Just go in the formula. There's another way to do this. I won't tell you though. I'll just do it like this because I can get away with it. Okay. So there's the formula with a 1. 0.189. We're winning. 0.189. And then I have to do 2. Second enter. Back up. 2. 2. 2. 0.441, making progress. And finally 3, wasting time, I think. Second enter, but this should be the only one that's horrible. 3. 3. 3, get out of here. Okay, 3, 4, 3, okay. So we're going to compute the mean. It's X times P of X. So 0 times 0.27 plus 1 times 0.189 plus 2 times 0.441 plus 3 times 0.343. If I typed everything right, we're going to get 2.1. Yay. So there is the summation of xp of x. So x times p of x mu is the sum of x times p of x up there. And then here's this crazy formula for the standard deviation. I take x squared times p of x, and I subtract off the mean squared. So let's see if, and then we take the square root. So x squared is 0 times 0.027 plus, then 1 squared is 1 times 0.189, okay, plus x squared 4 times 0.441 plus 9 times 0.343. So that's x squared times p of x. And now subtract off 2.1 squared, like that. The mean was 2.1. I get this giant, I'm praying now. If this doesn't work, I'm just going to go home. We just shut this down. I am recording this, right? I don't know. I hope so. 0.63, and then I take the square root. So half exponent does that. 7937. We win. Okay. So check, check. Okay. That was tough. Keep going. This will never end. Is there just 2 more pages? Oh, it just goes on forever. Well, we're not going to quite make it. That happens. I'll just keep sitting here and finish recording this once we run out of time. And I'll post it onto Blackboard. But that'll take a few minutes to do that. According to an airline, flights on a certain route are on time 85% of the time. Suppose 20 flights are randomly selected and the number of on-time flights is recorded. Great. Explain why this is binomial. Well, we said n is 20. We got p is 0.85. They're independent because they're randomly selected, and we're counting successes. You count the number. So yes, 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 and yes. Find and interpret the probability that exactly 14 flights are on time. Interpret it. In a large number of experiments of this type, we'd see about that many with 14 flights on time out of 20. We just go in here, we just use the binomial formula. 20, we go over to math, go over to prob, go down to NCR, we select, it's 14. 14, we come over, we go times, what's the probability of success? 0.85 to the 14. Come over times, and then 1 minus 0.85 is 0.15. And what's left over from 20, if you used up 14, is 6. So that's the probability of 14. 20, choose 14. Yep, it is, okay. There it is, 0.453. 0.0453 something. 7 maybe. Around 5% of the time, exactly 14 flights will be on time. And then do this, I'm not going to do it. We're going to sum the probability for 12, 13, and 14. In the interest of reviewing, I'm not going to sum it myself. I could put it in here. You just put 12, 13, and 14, and you have to put the right number over here so they sum to 20. Let's just keep going though, just for in the interest of making it to 10 after and maybe finishing. Don't think so though. According to an almanac, 70% of adult smokers started smoking before turning 18. Compute mean and standard deviation of the random variable x, the number of smokers who started before 18 in 400 trials. I don't know what this is here for. My scissors didn't work. So n is 400. P is 0.7. Oh, mu, it's binomial. We're counting the number of smokers. That'll be binomial. U is NP, sigma is square root of NP, 1 minus P. N is 400, P is 0.7. So 400 times 0.7, I could guess that is 280. And sigma is 400 times 0.7 times 0.3, and I have to take a square root, calculate that, and take the square root of it. 9.165. Would it be unusual to observe 320 smokers who started smoking before turning 18 in a random sample of 800? Here's the mean, 280. We're over here at 320. That's 40 units away. That's more than 4 standard deviations. We said 2 standard deviations is enough to be considered unusual, so 4 is basically impossible in most cases. So yes, more than, yes. 280 is more than 2 sigma from mu. Okay. Stopping sharing.